Okay, so I'm going to explain how to draw Lewis dot structures using Legos as a tool. So we're going to start by making the molecule phosphorus trifluoride, PF3. And to do that, we need a phosphorus and 3 fluorines. So I'm going to start by thinking about what is the Lewis dot structure for phosphorus and for fluorine, and how many bonds can they form? And then I will be able to use my Legos to figure out how they fit together. So phosphorus, if I look at my periodic table, phosphorus is right here in the same group as nitrogen. Now we previously drew in some Lewis dot structures, but let's say this was new, you didn't have a marked up periodic table. You could remember how many valence electrons phosphorus has by going all the way to the left and counting, because the first group has 1 valence electron, then 2, then we skip the transition metals, and then 3, 4, 5. So phosphorus has 5 valence electrons. And remember, we talked about how each side of the letter that we write, the symbol for the element, each side represents one of the orbitals you can put electrons into. And the electrons go one at a time until there's no empty slots left, and then we pair them up. So for the first four, we put 1 in each orbital. So like carbon has 4 valence electrons, 1 on each side. But phosphorus has 5, so one set of them is paired up. So phosphorus looks like 1, 2, 3, 4, 5. And you may have noticed on my periodic table, I sometimes draw little lines off of the unpaired ones to remember that those are the ones that can form bonds, covalent bonds. Now, on our Legos, we have learned that each little connector or stud on the Lego is 1 unpaired electron, 1 potential bond that can be formed. So phosphorus is the green Legos for us because they have 3 connectors, 3 bonds. Now, fluorine, if we look at our periodic table for fluorine, fluorine is over here, it's a halogen. And so if we count from the left, it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Or if you remembered the octet rule, if you start with 8 at the end, so we count backwards, so it's 7, that means there's just 1 unpaired electron and 3 pairs of electrons. So fluorine would be 3 pairs and 1 unpaired, so it can form 1 bond. And so if it can form 1 bond, that means it's our yellow Lego, or in some sets of Legos, they are white. But it is the single Lego that can form 1 bond, because remember, each connector is 1 bond. So for PF3, we need 1 P and 3 Fs. Now, in our sort of Lego rules of bonding, you can only have the Legos be 2 high, because only 2 elements can bond, not more than 2. And they must form a rectangle with no empty spots, because empty spots would mean unbonded electrons, which we don't want. And so it needs to be a complete, full rectangle with no empty spots. So this would be a way that we follow our rules, that it's a complete, full rectangle with no empty spots. And then the way we translate this into an actual Lewis dot structure is that each connection is one of our bonds, is a line that represents the 2 electrons that are being shared. And so I'm going to write the P first. And so each connection of the phosphorus to a fluorine, they're all single bonds because there's 1 connection, says 3 single bonds to 3 fluorines. Now with a simple molecule like this, you might think, well, why do I need the Legos? And maybe you don't. But when we get to more complicated ones, this helps make sure you're following the rules and doing the correct number of bonds for each element, and not, leaving any electrons around unpaired. But we're not quite done yet, because the electrons that don't pair are still part of this structure. So phosphorus had 1 lone pair that doesn't bond, and we need to add that on. And fluorine had 3 lone pairs. So we need to add those, because in the end, our structure should follow the octet rule, as in every element has 8 electrons around it, except for with the exception of hydrogen that only has 2. And then just as a little reminder, although we usually do just draw them as lines, it can be helpful sometimes to draw them almost as little like barbells to remember that each line is a shared pair of electrons. So fluorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and then the phosphorus 2, 4, 6, 8. We are double counting those ones in the middle, but that's kind of what a covalent bond is. They're having that tug of war that never ends. Both elements kind of feel like it's their electrons, so they both are stable and happy. All right, so that's the basics. I'm going to do one that's a little more complicated for those of you who are going to go for exceeds on this skill. And so I'm going to build C2H4O2. Now, when we add lots of atoms, there's usually more than one way, get my face there, more than one way to put them together, because there's just, lots of atoms, they could be rearranged. So each way they're arranged is a different compound. I'm just going to do one possible arrangement, but there's definitely more than one way to arrange these atoms. So carbon has 4 valence electrons, so it is our black Lego. Hydrogen has 1, so just like fluorine, it's the yellow Lego, because in Legos, remember, different colors aren't exclusive to one element. They show the number of bonds, and sometimes different elements have the same number of bonds. And then oxygen has 6 valence electrons, which means 2 of them are unpaired, and so that would be our blue Lego. So for C2H4O2, I need 2 C's, oops, an H stuck to that, so 2. Those are the oxygens, silly me. All right, so I need 2 carbons, 2 oxygens, and 4 hydrogens. Now, this is one that I've done an example before, and when I was thinking about it, I was thinking about acetic acid. So I'm going to make this make acetic acid. So to make acetic acid, I'll hook the carbons together there, put some oxygens down here. And now, oops, my carbons came apart. All right, now it follows the rules. It is 2 Legos high. It is a full unbroken rectangle. There's no empty spots in that rectangle. So now I'm going to turn this into a Lewis dot structure. I'm going to move this slightly so that I have room. All right, so to make this into a Lewis dot structure, I need to remember that each connection is a bond. So I'm going to start with this first carbon. So I'm going to write C for carbon. And this first carbon has 1, 2, 3 single connections to 3 hydrogens. So 1, 2, 3 single bonds to 3 hydrogens, just like that. Then its fourth bond is not to a hydrogen, it's actually to the other carbon. So I'm going to draw a single bond to the other carbon. Then this other carbon, the next thing it's bonded to, it's bonded twice to the same atom. It's bonded 2 times to this oxygen. So I'm going to draw 2 lines for a double bond to the oxygen. And then its last bond is a single bond to the second oxygen. Finally, that last oxygen has its second bond to one of the hydrogens. So that's my basic structure. And then the last thing I need to do is add in the lone pairs. Now carbon and hydrogen don't have lone pairs, but oxygen has 2. So both of my oxygens need 2 lone pairs. And now when I count my electrons, all the hydrogens should have 2, which they do. 1 bond is 2 electrons. Carbons should have 4, 2, 4, 6, 8, which is, each bond is 2 electrons. So 2, 4, 6, 8, 2, 4, 6, 8. And each oxygen should have 8, so 2, 4, 6, 8, 2, 4, 6, 8. So everything is following the octet rule. This is a valid structure. And like I said, there are other structures you can do. You can play around with it and try to do it yourself. But as long as it makes the rectangle with no empty spots, then it is a valid structure following the octet rule. Hope that helped.